on this drainage. Okay, so we have like 4 weeks left. So I already shared the content of the different lectures during these 4 weeks. So end of each week, you are going to have an assignment. Okay, and then so the lectures will be like 1 hour duration, right? So then once finish all the lectures, so you're going to have a test. So that's of course offline test. Okay, and then I think most of you might have seen this what you call the content. So if you are not, then please go through your chat box. So it's already posted. Okay. So if you we will start with the first first week will be covering like the effect of irrigation on salinity. So mostly, so in the previous module you have studied the irrigation, isn't it? So the good thing of irrigation is, so it helps in keeping the the environment healthy, as well as the improve the crop production. Okay. At the same time, if you misuse the irrigation water, that means putting a lot of water on field, so that definitely influence the different ill effects. So we are going to discuss that. And then the managing soil salinity. So once the soils are saline, so how to manage the soils by providing the drainage, we call artificial drainage. Okay. And then the third is the agricultural drainage and the components, which I'm going to explain. So if really you are, if you think that the artificial drainage is required for this particular, the land surface or the farm fields, so then what are the components, what are the types of land drainage? So all those things we're going to discuss in there. And then end of this week, so the field drainage layout. So the mostly will focus on the how to we put different components at different locations, and also how it looks like. So that will be discussed. And in the week number 2, we'll be discussing on field drainage. So mostly the drain pipe. So how to design a drain pipe, and then followed by structures, and then the design of drainage systems. So the groundwater flow hydraulics, we should know a little bit of groundwater flow hydraulics in order to understand some equations for simulating the water flow to the drains in subsurface as well as the surface. So then there is a surface drainage design. So we got two kind of design. One is hydrologic design, design. In the week 3, we'll be focusing on subsurface drainage design. We have different scenarios like steady state condition, the falling head, fluctuating water table conditions, and all those things we are going to discuss. So in different situations, how we are going to design a subsurface drainage. Suppose the water table is staying constant, right? So whatever flow is going in, so that's been going out. So in that case, how to design? That's a simple design. And suppose in irrigation, when you irrigate it, the water level comes to the surface. Then after that, during the course of time, the water level is going to be down. So that's called falling water table, right? So in that case, how to design a subsurface drainage system. So all those things we're going to discuss in that. And the 4th week, the last week, so we'll be focusing on the subsurface drainage design monitoring. Once you have laid the system, in field, then you need to watch what kind of difficulties you're facing, or what kind of malfunctions of the drainage system. So those things we'll be discussing in 4th week. And then so these are all artificial drainage designed by engineers, but there are some non-conventional drainage systems, mostly bio drainage. So it's a natural drainage we call. Like if you have some visit like trees, for example, eucalyptus. So these trees are also acts like bio drainage, so removing water from the deeper soil layers. All right. So if you have the drainage problem, so definitely there is a recommendation that you should go ahead with this, cultivating or the planting the eucalyptus trees around the field, so that the water will be, uh, water will be lifted up from the deeper root zone by these plants. Okay, that's a natural drainage, non-conventional drainage systems, and there are some worked out problems we'll be solving, and then the last there's a case study. So there are some, um, you know, practically install the drainage system, so we can bring that into the class, and we're going to see how they have what kind of problem and what kind of drainage system they designed, and what is the performance of that drainage system. So these things we'll be covering during these the 4 weeks. So if you have any questions in between, so you can directly email to me, or you can put it in the chat box. Okay. So am I clear? If you have any question, let me know. Otherwise, we'll go to start the lecture. All right. So this is today is the lecture number 1. As I indicated, we'll be discussing on soil salinity. I'm going to choose the pen. So this is lecture 1. Oh, it's so light, right? Okay, so this is the lecture 1 on soil salinity. So I'll be mostly using, the whiteboard for the class. So because that will help you rather than the PowerPoints. So I do have PowerPoint, but I think this is most effective way of doing things. So what is salinity? Why we are interested in this salinity? Right. So that's the important. What is soil salinity? We can mostly be focusing on soil salinity. Okay. This is called soil. Sorry. This is the soil salinity. So what is salinity? The first thing is. Okay. So if you see this globally, there are 950 million hectares of cultivated land is being affected by soil salinity. Around 950. It's a huge 950 million hectares globally, right? Hectares of global cultivated land is being affected by soil salinity. And then in India, so there are 23 million hectares. Look at this, 23 million hectares in India. So we also have this problem, right? And mostly the western part and the middle, and some part in eastern part. Okay, so I'm talking mostly about the soil salinity due to irrigation, or you can say anthropogenic issues. Okay, and then in India 23 million hectares, and this is going to account around 20 to 30% of cropland in India. of cropland. And this is growing. It's not that it stopped, it is stopped, it is growing again, right? So, and again, there are 14 million hectares of the cultivated lands are waterlogged. So these two are really main issues. Okay, so these two, one is salinity and the other one is waterlogging condition. So these definitely hampers the crop production or crop growth. Okay, so then here the whole idea is first we should understand the mechanism. So why these soils are being saline, and then what is the effect of the salinity on crop growth, and then how to manage the soils, soil salinity so that the crop production can be increased. So these are the most salient features of this course. Okay, so if you see what is why do we call it a soil salinity? Because if you see the soil contains some salts. So right, so the salts generally, the sodium. These are cations. We call cations sodium, potassium, magnesium, and then calcium. Okay, so these are the cations. If you see the anions, we have chloride and bicarbonates, okay, sulfates and carbonates. Okay, so it's not only cations and anions, it's combination of these two that constitutes the salts. Okay, so that means the soil contains not only plant nutrients, along with plant nutrients in the sense nitrogen, phosphorus and potassium. Potassium is a salt I just mentioned, but in addition to that there are some salts, that's sodium, magnesium, calcium, and chlorides, anions, both anions and cations. So these constituents should be at the limit, some limit. If the concentration of these, the ions are increasing inside the soil, definitely that welcomes the soil salinity. Okay, so then the next question is, so what are the sources of the soil salinities? How the soil is getting these, salts? So that's the next question. So in this, before going to that, I just want to emphasize on soil salinity, or we call saline soils. So the saline soils and sodic soils. There are two kinds of soils. So mostly, so the saline soils in this, the magnesium and calcium, these salts are predominant in case of saline soils. Sodium also will be there, but the mostly, the saline soils, the magnesium and calcium are more prominent or predominant than the sodium. Whereas the sodic soils, the sodium is predominant salt. Okay, so that's why saline soils and sodic soils. So then the question here is, so who is dumping these salts in the field? Okay, so since we are, I mean, there could be like two sources. Okay, so one is natural. So one is natural process, and the other one is anthropogenic process. Okay, so the natural process, generally you might have studied this weathering, right? So the weathering of parent material, weathering of parent materials. If you see some rocks contains these salts, right? So during this weathering process, the salts will come out, and that will be within the soil, profile. Then after that, during the uh, like irrigation, so or the evaporation process, so the salts are going to be migrated from lower or the from the place where it is to the the other places in the soil profile. So that's the due to the natural process, mostly the withering. The other one is anthropogenic process. So this could be, we are talking about the irrigation. Okay, irrigation is, so how the irrigation can add salts to the soil, because irrigation, that means we are talking about water. So water contains salt. So you might have seen in your home that there is a water filter. So if you ask the water quality of that, so definitely the guy comes and check the water quality in terms of TDS. It's called total dissolved salts. Okay, so just he wants to know what are the salts level present in your drinking water system. Okay, so the salts, it doesn't mean that it will give you a single anion or cation. It's like combination, it's overall, right? It's the total salts, remember, right? So that means the water contains these salts. Okay, so if you think that, if so, according to WHO, so up to 500 ppm, it's safe for drinking. So you're good. So he comes and check. Okay, so your TDS is around 600 ppm. So you need to change the filters, or you have to go for reverse osmotic process, the filters with RO system and all. He will suggest a lot of things. So that's the quality of water, right? If the irrigation water contains the salts, the concentration more than what it is recommended, so then there is a problem. So when you apply that irrigation water in the field, so that definitely that's going to welcome, or indirectly you're dumping salts into the soil. Okay, so that's one sources, one of the sources of the salts adding to the soil. Okay, so basically why we are irrigating? So irrigation, so generally, so irrigation has two effects basically, right? So one is it changes the landscape, or vegetation, and the second is it changes the soil moisture. Not only that, it changes the solutes in the sense all the constituents in addition to water. Okay, and then also it affects the groundwater. So these two effects, but at the same time, if you see, there are risks also. So I already mentioned what the risk is in my explanation. There are two risks. One is waterlogging and salinity. So this I already explained how this waterlogging and soil salinity is going to uh, going to be the part of irrigation, right? If you are not doing it correctly. So the effects, so when you irrigate it, so it's going to change the landscapes, vegetation. Okay, For example, you're sitting right at the Nalanda top floor, and if you look towards this side, right, there are a lot of agricultural fields, plots, and you feel like, very nice breeze coming out. So assume that there is no crop field at all over there. So it's like the entire, aesthetic sense will be different, right? Aesthetic sense will be different. So that's the contribution from irrigation. So since you are irrigating it, crops are getting enough water and growing well, and the evapotranspiration, I mean the water which is coming, pumping to the atmosphere as evapotranspiration, so that will really add this, nice, add moisture to the nice breeze, and that's where you feel like um, aesthetic sense. So not only that, it affects the soil moisture. So adding water definitely improves the soil moisture. And so this is important. So also it adds the solutes and improves the groundwater. So that's finally, once you add water on the top, it percolates down and meets the groundwater. And that's where the groundwater can rise up. And the risks are, waterlogging. So why there is water logging? Water logging and soil salinity, these are the two major issues we can consider with excessive irrigation or the bad quality of irrigation water. Okay. So for example, you have a field, right? This is an agricultural field, and let's say there is a crop which is here, and when you irrigate it with let's say Q1, that's a volume of water is being irrigated, and let's say this is the initial water table. I'm denoting with WT, water table. Okay, and there's a water which is going from the field, that's the Q2. So since you're adding water, so the water table could raise up, right? It could raise up, and maybe let's say this is staying here. This is the WT again, the new WT. Okay, let's say this is 0 and this is 1. So this is initial and this final, right? So it's coming and going. So suppose if Q1 is greater than Q2, so definitely the water, it will be adding to the groundwater, right? So that means groundwater is rising up, 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 and definitely since the water is not going, so that will be accumulated. So water accumulation, in the field. So that means what do you need? You need to have enough soil moisture within the field, and the excess water should be gone out. So that is the aim here. So this is the water logging example. Water logging, and suppose similarly you have a field. So you have a field, and you started irrigating with a relatively less quality of water. Let's say that the concentration I'm denoting with C1, the irrigation water concentration, and some concentration which is going out, that is C2. Okay, so definitely the constituents accumulation will be taking place if C1 will be greater than C2. So where C1 is the concentration of salts. Okay, we suppose the input salt concentration, if it is more than the output salt concentration, so the salt accumulation will be taking place. So that's going to add salts to the the area, and definitely influence the crop growth. now let's see how, so how to represent the salinity. So we need to understand what is the unit of salinity, how to represent salinity. Okay, so the soil salinity, so soil salinity is the index of concentration of salts in soil. Okay, so generally it is represented with electrical conductivity, or we call EC, electrical conductivity, EC. So the units are decisemen per meter, called decisemen per meter, or let's say millimos per centimeter. Okay, so since I have been mentioning this in terms of concentration, so how to convert this electrical conductivity in terms of concentration? Okay, so to convert the unit to concentration, that is in ppm. So ppm, okay, so ppm is the unit, we call it parts per million parts. Okay, million parts. So that means if you have million parts, so one part among the million parts is the ppm. So it's also denoted with milligram per liter. So in 1 liter, if you add 1 milligram of sugar, and if you mix it well, the concentration will be 1 milligram per liter, or that will be 1 ppm. Okay, that's a simple indication. You have a glass of 1 liter of water and add 1 milligram of salt or sugar, then stir it, and the concentration of salt or sugar will be 1 milligram per liter. Okay, so in order to convert this unit from electrical conductivity to concentration, we have like concentration in irrigation water, which is equal to 640 multiplied by electrical conductivity of irrigation water. So this is, I mean, there are different formulas, but this is approximately the conversion factor. So when you have a TDS meter with you, so next time if you observe, there are two units. One is ppm, the other one will be in decisemen per meter, or if you see the microsemen per meter kind of thing. So there are two. You can check a TDS meter when you check the quality of your drinking water. So the two. So this will be like ppm, and this will be decisemen per meter. Okay, in order to convert this. So remember this. And then, for example, so let's just visualize how, suppose if you are adding an irrigation water with some concentration on 1 hectare of field. So let's say this is just to visualize how.
Excuse me, sir.
Sir, you are not audible.
You are not audible. Or it's been while. Did you press anything? Am I audible now?
Yes, sir.
Yes,
Okay.
sir, you are.
Yes,
So
sir.
it just happened now or before? I mean, how long I'm not audible?
Sir, like just after you finished explaining that relation between
Okay.
Concentration
Thank
and
you.
vector conductivity.
Thank you. So this one, right? CIW.
Yes, sir. Yes.
Yeah. Okay. So now let's
Yes, sir.
visualize. Well, let's visualize. So suppose if you have an irrigation water with some salts concentration TDS, right? Let's say ECIW, that is electrical conductivity of irrigation water. So that is 0.6 decisemen per meter. So that's the salt content. So let's say you have applied. Sorry. So you have applied a depth of like let's say the D depth of irrigation is equal to 600 mm. So this is the depth of water you applied through irrigation. What is the area? The area of the field will be 1 hectare. So the question here is, so what is the mass of salts added? Okay, it's a simple question, right? So the first thing is you need to, because this is in decisemen per meter, so you need to convert that into milligram per liter. That will be more easy to multiply with the what you call this the problem what we have right now. So in this case, so whatever the value we have, we can calculate the volume. Suppose this is the area of the field, and so the depth is, let's say the depth yeah, so this is the depth, right? So the depth here is 600 mm, and this is 1 hectare. 1 hectare field, 1 hectare in the sense 10,000. So this is the volume. V is equal to 600 mm, right? So that will be by 1000, that's in meters, multiplied by 10 power 4. So this will be your meter cube. That's the volume of water you applied into the field. Okay, so knowing that volume, so next is you need to convert this into ppm. Now EC IW is equal to 0.6 decisemen per meter, or 0.6 multiplied by 640, and that will be 384 milligram per liter. So in 1 liter of irrigation water, there is 384 milligrams of salts. We have the volume here. So this is the volume of water. That's not 1 liter meter cube. So again, you need to convert that into either liters, or maybe 384 milligram per liters should be converted into milligram per meter cube. So let's see. So one volume unit is there in both sides. So if you can multiply these two quantities, then you get the milligrams. That's simple. Okay. So now volume, let's say the volume will be around 6. So 2 gets cancels out, and then 6,000, right, meter cube. This is 6,000 meter. So amount of salts. So let's say salts, that will be 384. That is milligram per liter. Okay, and then 10 power minus 3. So let's convert into kg per meter cube. So milligram per liter, if you convert into kg per meter cube, you have to multiply with 10 power minus 3, and then 6,000, and you get this meter cube gets cancels out, and finally what you get is 2304, sorry, 2304 kg. So this is the amount of salts you are adding to the field. Okay, this is just to visualize. I mean, it's a simple calculation, but powerful message. Okay. So the next is, that's okay. The salts are there. You are adding salts to the soil. So what is the effect of that? How the salts are going to affect the plant growth? Because unless you understand that, I mean, it's a difficult. Like you don't care about salts, right? So how salts are going to so we call the effect of salts on plant. So whatever the salts you applied, that should be removed first of all, right? If you do not remove it, and how that's going to influence the plant growth. Okay, so uh, so suppose if you have a field and you have a plant. Okay, let's say you added the irrigation water, right? That contains concentration, let's say C1. So you started adding it. So what happened? So the water, anyway, these are the dissolved concentration I'm talking. So the water will be added to the soil, okay, and the salts will be, accumulated around. Salts will be accumulated because it contains the salts. But how the salts are going to influence the plant growth? The plant, the purpose of plant is to extract water and nutrients. So that's what, if you go to your home, so what exactly you require? You need water and you need some food, right, for your survival. So similarly, so for the plants, the soil system is the home. Okay, so the plant requires the water as well as the nutrients as a food. So what are the nutrients? Phosphorus, nitrogen, potassium. These are the major nutrients, and there are micronutrients too. Okay, so these things are required in order to develop their physiological growth and then biomass and all. Okay, so what happens if there are some salts present around? How these salts are going to influence the, let's say now our focus is on water uptake, right? It's supposed to take out the water through transpiration, right? And some, let's say this is evaporation, and both together you get evapotranspiration. So that's what water, you get water from the soil if you have a crop field. Okay, that's the ET, total evapotranspiration. But how the evapotranspiration is going to influence the salts present in the soil? So that's the question here. Okay, so you have to remember one thing. So whatever, so definitely that's going to affect the water uptake. So whether it will improve the water uptake or decrease the water uptake. Anyone?
So can you repeat the question?
The question is, so if you have salts present in the soil, right? So does that improve the plant water uptake or decrease the plant water uptake?
Decrease.
A decrease, sir.
It will decrease, right? Okay. If this is going to decrease, then how that's going to decrease? So what process? So we call that process as osmosis. Yes, you're right. Right? This is osmosis. So the osmosis, that means suppose if you have a solution which is separated with a membrane, okay, so let's say you have a salt solution here and you have a, let's have a less concentration, not much. So here the concentration is C1 and C2, and if you have like C1 is greater than C2, so in that case what happens? So the water will be transported to the next tank, that is through osmosis process. Okay, so the level here will be increased. This level will be increased here. Water level will be increased. So what is osmotic pressure? Osmotic pressure. So now your term is you have to push this. Sorry. So you have to push. Sorry, push this level down to the original level. So during that process, the pressure required to push this, yeah, push this level down to the same here. So the pressure required will be osmotic pressure. Osmotic, right? This is osmotic pressure. So why this is important in here in the plants? If you see the plants, so the plant has the cell membrane, right? If you see this, so the roots are going to suck water through the cell wall. Here the cell wall is kind of a membrane, right? Cell wall is kind of a membrane. So what happens, the salts are present here, and let's say the fresh water is inside the roots. So it's going to happen instead of taking water from soil. So now the soil system is going to suck water from the plant body. Okay, so that means this reverse is going on. So definitely that's going to affect your plant growth. Okay, so there are two things here. Atmosphere, it acts like a pump. So because this is the demand, atmosphere is demanding ET because of the temperature and all other things. So I mean humidity and all. This is demanding. So it's like there is a system here. There is a system and someone is pumping. Okay, and here this guy is reverse. It's very difficult now compared to there is no salt. Suppose there is a no salt case, it's easier to take out water, but in this case it's difficult to take out water. So that definitely influences the plant growth. So the salts should have a definite concentration. If it is more than certain concentration, definitely that's going to affect the plant growth. So now, so osmosis pressure or osmotic potential. So the osmotic potential, so that's been measured or estimated, the psi naught we call. So that will be, there is a formula, so minus 3.6 into electrical conductivity of saturated soil extract. So this is called ECEs, EC of, sorry, this is EC of saturated soil extract. Okay, so what is saturated soil extract? You take a soil sample, saturate it, and then you find out the electrical conductivity of that. So how do you get the electric conductivity of that? So you have to extract that water. So it's like we have a centrifuge. So you take out the soil sample, saturate it, put it in a beaker, and on centrifuge, and run it for an hour, and whatever the salts attached to the soil particles will be released into the water, and that water, if you can filter that water and find out the electrical conductivity, so that will be ECE. Okay, so if you have that number, multiply with 3.6 and you get psi naught. Okay, so that's in meters. So this will be in meters. Okay, and this will be in decisemen per meters. All right. Okay, so the next is, so if you see this formula, so this formula, I'm sorry, so this formula is tagged to soil moisture. So if you have a soil moisture difference, the same formula will be like this: ECE multiplied by theta S by theta. So generally we denote the soil moisture in volume basis as theta. Theta is soil moisture in volume basis. It could be a fraction or like meter cube by meter cube, centimeter cube by centimeter cube, so like that. So theta S is the saturated soil moisture and theta is the current soil moisture. If suppose if it is saturated, so theta will be theta S and this will be 1 and you get psi naught for the saturated case. So what happens if theta is decreasing, right? If theta is decreasing, so that means, so this minus sign will increase, right? Minus sign will increase. That means the suction is going to increase. Okay, so that means soil has potential. Soil has potential to hold with that pressure. So it's like two persons are grabbing for water, let's say. The plant is one person and soil is one person. So when theta is decreasing, so that means the advantage is with soil. Soil is going to, grab. And the plant's time is to put more pressure in order to extract water, right? So that's the difference here. All right. So I'm going to stop with the last example, right? So this is
Excuse me, sir.
yep.
Sir, can you please explain that, like, what is the difference between the two formulas you wrote? When are they applicable? Yes, sir. Sir,
Yeah.
in the first one, you just wrote minus 3.6 into ECE, and in the second one, it's into theta S by theta. So, what is the difference?
So the difference is when you have, when you consider the soil moisture into picture, so then you have to multiply with this fraction theta S by theta, or relative moisture content we call, right? So this generally, soil moisture plays a big role in because ultimately the water is a driver, right? Water is a driver, right? Any solute to move from one place to another place, there's a water. So that's why, so this equation plays a big role. So if you have saturated case versus, getting dried case, like theta is getting dried, that's how that's going to, affect your osmotic potential. So this will, I would suggest you have to go ahead with this first, right? So then if suppose no information is given on soil moisture, so definitely you can assume that the soil moisture is theta S. So the theta is theta S. If there is no soil moisture is given in the problem. That's the only difference. Okay. So the example here. So suppose if it is given theta S. So theta S is given as 50%. Okay, and theta is given as 25%, and ECE is 1 decimeter per meter. So in that case, what is psi naught? Psi naught is equal to how much? So that means an irrigation water, sorry, not irrigation water. A soil has a salinity of 1 decimeter per meter. So this is the salinity level in the soil. And then if the psi naught will be how much? If suppose the soil moisture is decreased from 50% to 25%. So in that case, you just use this equation 3.6 multiplied by EC extract multiplied by theta S by theta, and that will be minus 3.6 into 1 into 50 by 25, and you get the minus 7.2 meter or minus 0.72 atmosphere. So minus 0.72 atmosphere. How do we know whether this is going to hamper your crop growth? if you remember your field capacity, let's say the field capacity. So what is the pressure at the field capacity?
15 bar.
What is that? Atmosphere. Let's say atmosphere. That should be like, in order to extract water at the field capacity, it should be like a 0.33 atmosphere, right? So if you see this case, it's easier for plant easily can extract at this pressure, but the pressure is really increasing here. The negativity is increasing almost double. So that definitely that influences the water uptake with the plants. Okay. So I'll stop here and we'll discuss in the next class. So we're going to talk about the salt balance. Suppose if you have salts added in different means. For example, irrigation water, uh, let's say to fertilizers. Fertilizers also contain salts. Okay. So then groundwater also contains salts. So suppose that is also adding to the system. So here our control volume will be the plant root zone. So suppose if we have the plant root zone, right, as the control volume, so we would like to see what are the ins and what are the outs, right, or maybe ins. So then finally we're going to see the balance. So the next class we're going to talk about that salt balance. Okay, and then we knowing the salt balance, we'll know how much water is required to leach the existing or accumulated salts present in the soil, because this is an engineering problem. Okay, so you should understand that. All right, any questions before I close? If no questions, then let's meet on Wednesday at 8 o'clock. Okay.
Thank you, sir.
You're welcome.
Thank you,
Take care. Bye bye.
Yes, sir. Thank you, sir.